Thanks again for having me. My name is Heikki Nousiainen. I'm a co-founder, CTO at Aiven. And I'll just as mentioned, I won't go into... There we go. I'll do a quick intro on what do we do at Aiven and how it got founded, just to give a little bit of a context on the rest of the presentation. But we are indeed a managed service provider for open source data technologies. Aiven was founded in 2016. We started as a Postgres as a service company. Me and my founders worked a long time in software industry, and we're kind of going through that phase when cloud became an option, and we started to move from perhaps operation-led organization into more of a DevOps mode, more in business line driven development. So one thing that was really important to me was developer productivity, being able to do stuff and start projects and see how they go and fail fast, throw the ideas out of the window if they didn't work out. Me and my co-founders, we were quite good at running Postgres at the time. We did build a lot of automation around that, and we were able to launch our projects, but then we faced the problems on it's not production ready. There's no one to run it. No one wants to run Postgres because it's not commercially supported. Our peer teams perhaps didn't have the same experience with Postgres that we did. So we started Aiven on that idea that, hey, let's make it available for developers like us and kind of try to make life easier for folks like us. Since then, we've grown to that global, serving over 1,000 customers across the globe. We have moved quickly from that Postgres as a service into a whole suite of different open source technologies, going across different use cases, different business problems that can be solved with this. And we like to think that it's important to have the right tool for the job. And that's why we are providing a platform of services instead of trying to convince everyone that Postgres can solve all your problems that you face. But really, a managed service out of these technologies. Our heart is really with the open source. That was one of the aspects of that we wanted to help adoption of open source for the values and for the freedom that it gives to users. I won't go into this again. I'll drop a quick reminder. I was asked to do this, so check that out. Open source data infrastructure meetup available here in Helsinki, but also around the world. So if you happen to be traveling somewhere, check us out. Or if you want to talk in these events, then also get in touch. But Python at Aiven. So myself, I come from a software engineering background. Before we founded Aiven, I worked I've been in software for 25 years professionally, half of that being roughly in C world in compiled languages, and then found Python through kind of first as a testing framework, and then through a lot of tooling around how we could help to build pipelines that we didn't necessarily need to write those in bash scripts or shell scripts anymore. I love Python. That links to my saying that productivity drive for the developers. I believe that Python is for the productiveness and for the maintenance or maintainability that gives to developers. It's great. And at Aiven, serving those over 1,000 customers, we almost exclusively use Python in our operations. So there has to be a very good reason on utilizing something else. And those might be, maybe we need a plugin for Apache Kafka that it's built with Java, then we need to go there. If there are some, I'll get to that later, then we have some corner cases where we use Golang to get some performance concerns out of the way. But this talk is a little bit given what do we do with Aiven, and then some of the practices that we've done to make that development sustainable and working with Python. quickly for context, Aiven architecture, we have a control plane that is here on your left, that is shared among all workloads that we run, and that contains database, is a system of record keeping track of all the service subscriptions. We have execution agents that work on tasks to make sure that those services that we implement for our customers are up and running and healthy. I will go to some of these a little bit later. Then on the right-hand side, there's the data plane. When we started building Postgres, we wanted to ensure that you get all the guaranteed performance. So we use a lot of virtual machines to implement these services. So one Postgres cluster equals one underlying virtual machine, and all of those guaranteed resources. Same for Apache Kafka clusters. One broker equals one virtual machine. So with that fleet, we are operating a lot of service agents, independent service agents here. But both these sides work or are built with Python. A couple of principles on how do we operate. We at Aiven, we consider everything needs to be code. So that includes not only the Aiven operating system or the automations that run these services, but looking at things on how do we prepare infrastructure, how do we do operations on instead of logging in and doing a change, then build a tool around it. It goes into managing our dev and test CI pipelines, and everything that we do, first and foremost, should be code. And that's kind of something that drives with us, and that has I'll soon mention, has a very strong link to what Python can offer. We operate everything on a converging operation model. So everything in our state changes is constantly looking at whether the actual state is matching what we expect it to be. And if it's not, we take corrective actions towards that desired state. And that helps us a lot with control loops and managing things the way we do. Then we distribute everything for, first and foremost, for high availability. We work in cloud. So today it's probably much more reliable than what it was 10 years ago. But still, you have to account for all kinds of weird issues or network breakages or wrong configuration or shooting yourself in the foot and doing some odd operation that didn't go exactly as planned. Scalability on the same side, thinking at every moment on how we can split the work between kind of components that we can multiply instead of trying to build something that just runs those cycles faster and faster. With those instances, we believe very much in the immutable infrastructure, similar model as you would do with containers. So you launch them once, you never do any in-place upgrades, any modifications, but rather just if you need to add something or update a piece of software, then you replace it altogether. And this is for us to ensure that we know the exact state of whatever we have deployed and that we can verify that we've given quality control on every combination that we launched. But it also has the very nice side effect that now we can run with the most modern software versions available everywhere. Going into, I'll just share some numbers, and this is more of a motivational from Python. I've heard a lot that it's not enterprise ready, and in my projects in the past, it was especially looked down by people that were then running it in operations. So this is want to highlight that Aiven runs on Python. So to put that fleet serving those 1,000 customers, we are running 140,000 virtual machines across 7 cloud providers and across about 150 regions across those providers altogether. And this is built on primarily on Python. We have about 150 people in software engineering and then software site reliability engineering side of things. Again, we consider everything code, so these are all software engineers for us. Aiven Core, we From our history, we are running most of the things from one single monorepo. This is due to history, but it also gave us very good guarantees that whatever that we integrate, we can test together and verify before we deploy something. Now with the engineering, it starts to be a little bit something that we want to change, but regardless, the size of our operations, about 200,000 lines of production code and then 60,000 lines in testing. And again, this is in Python. And just kind of a sign of our velocity, it's about 5,000 code commits, excluding merges during the first quarter, and 2,900 individual pull requests merged into our mainline during that same period. So quite a lot of volume there, and I think that part of this is because Python is so productive. And we are now running with Python 3.11 and looking forward to moving to 3.12. This is mostly we track Fedora packages, and we're now a little bit behind the latest Fedora development. All right, then why Python? So this is coming from our background from the founding team. We really found out that Python was super productive in going from prototypes and going from experiments and trying out things and then expanding that into something that is production quality. So it really makes it easy to do experiments. You don't have to manage compile chains and all kind of things, and adding a small change is easy to do in different types of systems. On the other hand, maintainability. We love the Python's kind of eliminating all the necessary scaffolding and just making things pretty. And we believe that that really makes it easy for other people to approach and understand the thinking on how people have perhaps thought that implementation before. Code conventions go to some extent in different languages towards this, but at least I'm in love with Python. I think that that's the best implementation so far that I've worked with. Wide range of libraries, especially for us, we work with a lot of technologies. We get not only a rich set of libraries, but many of these libraries are nowadays packaged and maintained by Linux distributions. So, for example, and when we find something that is not packaged, all the distributions are quite welcoming, including packaging script for technologies that are missing. So. Definitely enjoy there not having to invent or not having to invent things yourself, or not having to find a source from some weird place. Now, versatility is definite value. I mentioned that it's not only our code, but we run everything through that Python. So it's everything that we manage. Our infrastructure is essentially code. That's our kind of contract. That's our request for comments on doing changes to environments. We run our CI with Python. So every developer then can contribute to areas when we see that, okay, this test run starts to slow down, or maybe we can find some clever ways on testing only the or through dependency changes, then everyone can contribute and pitch into that side. And then there are the typical ones. What about performance? Performance with Python has never been an issue for us in the large scale. There's certainly areas that we need to then take that into account, but our operation is mostly I/O bound, mostly network bound anyway, so it doesn't really matter on getting the top-notch performance. So productivity, maintainability goes far beyond that in value. And then perhaps coming up every now and then is the FinOps side, the sustainability side. That is it true that you need to use more cycles to run Python programs? Well, for us, again, this is not really a concern because we're not CPU bound to begin with. And when we are CPU bound, then we can start to take a look at on how to optimize that part away from the picture. So some of our experiences next on how to make Python work in our context, and hopefully you can find some something new or something that you can share forward from this. So first thing I would just in general recommend on every time working with Python is really to understand and classifying the workloads, seeing what are the best fits. There's already a lot of different ways on how to handle say concurrency with Python, and just understanding what needs to be interactive, so the user can't wait for a response. You need to have immediate response. What could be batched? If there are background works, or if you can organize that you can place an order and then ask for a status that how that order is ongoing. Maybe that's one way of getting rid of that kind of strict interactive, strict real-time requirement. Understanding what loads are IO bound and what are CPU bound. Quite obvious, but I think Python excels in nowadays with IO bound workloads as well. Hopefully I have an example there soon. Understanding what is stateless, stateful. Our Python is completely stateless. Then we use Postgres or Apache Kafka or OpenSearch or the other technologies to complement what we do within Python to make things click. What needs to be ordered, what needs to be at opportunity. I have an example on this, what this means in more, but in general, how do you handle requests and how you handle tasks? Does it matter? Are there interdependencies here? And more you can relax these, or more than you can offload these to some, let's say, a proper work queue systems, for example, the more easier it is to build concurrency and thus performance. And then we deal with things that time to complete, some cloud actions take ages before the API returns. So we need to account for that. Some things that are firing right away, and kind of just need to make sure that we optimize and understand what are the splits here. And then the need for level of concurrency. But based on our finding, it's just kind of trying to look on places where we can distribute and split the work in these different categories, then makes the overall performance work well and overall systems work well. Regardless, we love Python, but regardless of the language, to be honest. We do hit performance issues quite regularly. And then it's just a matter of engineering and looking into those and provide or digging into them properly and finding a way what is the cause and what is the true bottleneck in those cases. And then you have options. Then you can run something in out of process altogether with some command line utilities or whatever it is, or then just implement something natively and call them from the library and extensions and run that code. That is the bottlenecking one in native mode. So a couple of examples here from us. I need to check time. So we have in that picture we had that REST API, and for our customers that is then critical. That needs to be interactive. We get a lot of requests, so we need to figure out how that happens. Most of those requests do some kind of a call to a database that is probably slower than what the CPU can do. So this was for example, implemented in asynchronous Python altogether, and gives us great performance. We have then further split this into multiple processes and running on multiple virtual machine instances, for example. And by scaling the number of these workers, we can handle, or at least so far, we've been handling the quite aggressive growth that we've been able to do. Some of the things that we needed to know, there are some transactional dependencies here. When customer makes an order for subscription, it needs to be returning from all the instances that are, or the next API call needs to get a sensible response. So here for ordering, we are just actually relaying that a bit to Postgres transactions and then maintaining consistency there. Not even trying to do cross-node synchronization here. And for offloading, one obvious one is TLS termination. Doesn't make any sense or at least for us, it doesn't make sense to run that in Python, but just give that out and concentrate on the business logic. State updates coming from the workload nodes, the 140,000 instances, we just thought or realized that we need to persist this in Apache Kafka or some system. The instances can come and go at any point. We might not be able to process the events real time. Make sure that we have the persistence on, that the client can be rest assured that the message is stored somewhere when it gets an okay from the API. And then we have a whole bunch of workers that read on that Kafka pipeline and then act on those messages. And if we have some errors, in some transit errors, network outages between the worker and a database, for example, then we can always restart those tasks that have not been completed. Kafka is an interesting story. We had quite a lot of clients connecting to Kafka cluster, and then it on stable state works quite nicely. But then when something goes wrong, all the 100,000 clients came on calling, and with Kafka they came calling on multiple brokers at once. And if any of those connections failed, then they would start over and create additional connectivity. So this is the example where it's not. Performance issues are not specific to any one language. It's more on looking at the implementation as a whole. We ended up changing the protocol, building a proxy in front of the Kafka that talks just regular REST interface, and then we can handle on the client side all the error cases much more easier and much more in a kind of saner way than let's say the Kafka clients that are out there. But here, current implementation is Golang, but we validated and really perfected the whole signaling channel with Python before we moved to Golang for performance reasons. And finally, task execution agents that then trigger actions. These are things that are provisioning cloud instances or going onto the cloud instances and doing the setup tasks to get everything running. Here is a wide variance in time to complete. So from the time that we start an instance in cloud, we are to where we are able to SSH into it and do the setup tasks. Versus we do a delete action that returns immediately. So here we needed to start to look at the different task executors that we split them up, because some of them are not time critical, some are, and then kind of figuring out what are the right ways to split this to make sure that we have the right amount of those agents to maintain the right amount of concurrency for each of the tasks. And all this is kind of a little bit ongoing effort then on tuning the system and making stuff happen, but works perfectly well with Python and perhaps our ability to react to these performance issues is even better with Python. All right. And looking at a couple of recommendations from our operational feedback, everything breaks all the time when working in kind of the number of versions, number of things that we're working. Either it's our code or then we get an unexpected response from one of the cloud APIs or something of that happen. It's really hard to test truly the less used paths of the code, especially error handling. So this has been really great for us that we are actually underneath many of the systems. We are catching all unhandled exceptions and sending them right through to Sentry service. And with Python, compared to some of the debugging sessions on looking at core files or most often not even having the core file and trying to reproduce a very small error or a very rare error case, Python, we get the ample of information through these exceptions. And we usually pinpoint the exact error even without needing to reproduce anything or needing to even look at the system that failed itself. But we can, from those errors, we can usually deduce and find out what's wrong. Similarly, we use a lot of counters and a lot of instrumentation to understand the behavior when it's out there. So we have a lot of expected behavior, but maybe that's something rare. So those might be transitional errors or some kind of weird responses or truncated responses or something that we handle, but shouldn't really happen. But with capturing these with counters, we can keep tabs on that, send them to InfluxDB or something, and using Grafana for dashboarding, monitoring, and catching those before any of those issues become a problem. And last not least, we are now a big friends of feature flags. We used to get away without having these when we were doing daily deployments with a small set of items. Now with this volume, our CI pipelines are not fast enough so that we can respond to things happening out in the field with the same fashion. So everything that we nowadays do, we try to implement feature flags for us to be able to control then the behavior after deployment. If we see any errors or vice versa, when we validate something that maybe this works better than the previous implementation, then gradually shift more and more usage towards the new setup. Last but not least, then looking at some of our practices on the development side itself. So obviously nowadays everyone has all the CI pipelines, automated testing, PR flows defined. All or most of this stuff is all those tests, all of those CI implementation or drivers are part of our core software offering. So any change that is done to either code or to our infrastructure goes through the same processes on people reviewing those changes and making sure that they make sense and that they are maintainable. Code conventions, we are very opinionated on how things should look, because then it makes so much easier for others to maintain and learn on what was implemented here and where. But rather than doing documentation, Python has a rich set of automatic linters and reformatters that it's easier to define a configuration file that dictates a certain style across everyone, and then just argue on how things should be looking like that. I become a big fan of typing. I've fell in love with Python probably because of the fast development cycle, and then jumped into having a huge dictionaries that could be understood by newer versions and maybe ignored with the later ones. But now we have a mandatory policy on using strict typing on all the new code that we implement. And we found that really useful on finding bugs from those seldomly called paths, and also making sure that it's things are, again, easier to understand. With IDE, you get understanding what is and autocompletes on what is actually the developer intended things to happen, instead of having to try to guesswork and go figure out from that way. And then I recommend use then these strict enforcing testing tools as part of the old CI cycles, and early as possible, not even having to go in those discussion on whether something should be typed or not. We have one last great example on this, and this is something I'm really hoping that Aiven can open source again, or open source at some point. So we went ahead and we're using a lot of function API calls in Postgres. So all of our components, when they interact with the database systems, they don't get access to the actual SQL, but rather a function API that then implements things like transaction underneath and access controls and so forth. But one of my colleagues went on then to implement a parser that parses our SQL, the function code, and generates Python typing classes out of every call that we make. So now that we can actually get automatically typed responses for all the queries that we perform in database. And this has been super helpful in making sure that we can maintain the velocity that we have in the development that we have. All right, I think I used Did I use even a little bit more? But happy to take any questions, or then now, or then anytime later this evening. Thank you. I hope you found some of that useful.